So as we start into our last unit, which we go over Chapter 8 and one section of Chapter 9, this gets into dealing with probability distributions and statistics. Very basic statistics. We're not going to get into the types of things you would see in a statistics course. We're gonna learn how to, under different circumstances, come up with a mean, a standard deviation, and so forth. Whereas in a statistics course, you would use that information to determine certain things about your data. We're not going to go that far with it. We're basically just going to look at different probability distributions given certain circumstances and how to find means and standard deviations and other basic statistics from that. So as we get to 8.1, we're going to look at distributions of random variables. So basically, a random variable is classified into three categories depending on the set of values it assumes. A random variable is called finite discrete if it assumes only finite many values. For example, random variable x is a finite discrete because it only has a finite set of numbers 0, 1, 2, and 3. You have an infinite discrete variable, which basically there's infinitely many values that can be arranged in a sequence. Basically, whether it's finite discrete or infinitely discrete, your discrete variables are counted. I can count them. So if I had like an endless amount of different integers, that would be an infinite sequence and so forth. A random variable is called continuous if the values it can assume comprises of intervals of real numbers. Typically, continuous variables are measured. So, like if I'm trying to compare the number of people who like something, that's a discrete variable. If I'm looking for the number of times that this thing occurs, that's still, a discrete variable. If I'm looking for the height of plants I'm growing or anything of that nature, like the length of something's movement or whatever it may be, where I have to measure it, that would be a continuous variable. So for this first example, you have 3 balls are selected at random without replacement from an urn containing 4 green balls and 6 red balls. Let the random variable x denote the number of green balls drawn. So you want to list the outcomes of this experiment. So basically, if x is the number of green balls drawn, and I'm drawing 3 from this urn or whatever it's called, I'm going to have x could be possibly 0, 1, 2, or 3, where x represents the number of green balls that I have in my selection. Now find the value assigned to each outcome by the experiment. So I want to find the probability of each one of these. So first of all, I'm going to determine, how many different outcomes I could possibly have of selecting 3 balls from the sample size here, and that's going to be basically 120. Whereas, given the certain circumstances, the number of ways I can select 0 green balls would be 20. The number of ways I can select 1 green ball would be 60. The number of ways I can select 2 green balls would be 36. And the number of ways I can select 3 green balls under these circumstances is 4. So when I make up my probability distribution, the probability of 0 is 1 out of 6 when I simplify. The probability of getting 1 green ball is 1/2. The probability of getting 2 green balls is 3/10. And the probability of choosing 3 balls in 3 selections is 1 out of 30. And so when it says find the event compromising the outcomes to which a value of 3 has been assigned by x, it's basically just asking me for the probability of 3 green balls selected when I choose 3 balls from this urn. And that's going to, of course, be 1 out of 30 or 0.03 repeating, or just the 3 repeats. And another example, let X denote the random variable that gives the sum of the faces that fall uppermost when two fair dice are cast. And we talked about this probability distribution before, so it's not a big surprise that here it is again. And they want you to find the probability of getting a 7. Much like it was before, I can see from this table the way it was set up, it is a 6 out of 36 chance or a 1/6 chance. So for example 3 here, we're looking for the probability distribution of the random variable x, which is shown in the accompanying table. So now we have a table here where x is representing things. Now I have these values, -10, -5, so forth and so on. I don't know what these actually mean. They could be like, like negatives means I'm losing money, and 0 means I'm breaking even, and 5, 10, and 15 means I'm getting that much money. I mean, they can mean something else. I mean, it's really hard to say what they mean, but but basically here, if I'm given this kind of table, well, one of the first things you should always kind of do is make sure that your probabilities add up to 1. And this does in this case here, but you should always be kind of on the lookout for that to make sure that you do have a probability distribution in front of you before you start making conclusions from it. So if I look at this table, I could see that the probability that x equals -10 is right here, just from this piece of data right here. So no surprise that that's going to be 0.20. Now here I'm given a range of values. So I want the probability that x is between -5 and 15. Now I could see right here, that's circle there, is where, the data is going to come from. And so basically, once I have this table in front of me, all I got to do is just add these all together, and I would get 0.65. The probability that x is greater than 0, well, I'm looking at everything here into the end here, not including the 0. I was kind of hovering over that before. It says greater than, so it means I'm not including 0, so anything more than 0 for my x values. So these 4 pieces of data add together. When I add them all up, I do get 0.6. And the last one says the probability of x less than or equal to 20. Now technically it's all of these things here. And I can add all those up, or I can simply say, okay, well, I have 0.15 here. If I do 1 minus that, it's going to be 0.85. So, and you also find out if you add all these together, you also get 0.85. So one way or the other is fine. A histogram is, some people just think histograms are just bar graphs. They're not. I mean, there's different types of bar graphs. A histogram is basically a graphical representation of a probability distribution. The other thing that's different is instead of having probabilities, it's usually listed in counts. How many are in this group. I can come up with a probability distribution from that pretty easily. But basically, that's what a histogram is. It's a graphical representation of a probability distribution. So we look at example 4 here. You're given this data by customers waiting in line in the express checkout at the beginning of each 3-minute interval between 9 a.m. and 12 p.m. on a Saturday. So basically what this is kind of saying is, if I look at the data here, under the horizontal axis 3, that means basically, how many, 3-minute intervals were there where I had 3 customers waiting in line in the express lane, and this is telling me that there was 7 of these 3-minute intervals in this study that had that happening. So that's what the data means. So what you're asked to do here is create a probability distribution based off this histogram, and then find the probability that given any 3-minute interval in the study, there's at least 2 and less than 6 customers in line. The probability that of these 3-minute intervals, there's between 7 and 9 customers in line inclusive. And for D, the probability that given any 3-minute interval in the study, that there is at most 4 customers in line. So you're going to make a probability distribution. I'm not going to be asking you to submit that because there's no way for me to give you any kind of feedback on that. But you're going to use that to come up with your answers for these probabilities. So as we go through this, make sure that you are giving the right probabilities for B, C, and D, and that'll kind of let you know if you're on the right track or not. So take a moment and do that, and we'll go back over it momentarily. Okay, so the first thing I need to do with this is I need to, I'm going to focus on part A right now. I want to create a probability distribution for this histogram. This horizontal data down here is my X values. And that stands for the number of people that are in a express checkout line at these 3-minute intervals. So it ranges from 0 to 10 at the most. So X is going to be the number of people in line for each one of these intervals. I know that I could go from 0 to 10 because I can see the range of values. Now what I also need to know is be aware of, well, how many 3-minute intervals are we looking at here? Well, I can kind of tell that by just kind of adding all these counts together. I have, 1 here, 4 here, 2. And this basically is reading the histogram. And so there's 60 of these 3-minute intervals between 9 a.m. and 12 p.m. that we looked at. And it kind of makes sense. I mean, because, if I look at, basically 9 a.m. to 12 p.m., that's 3 hours. 3 hours, is 180 minutes. And if I'm looking at 3-minute intervals, 180 minutes divided by 3 minutes is going to give me 60 of these intervals. So it kind of makes sense in the long run. So, and now what I'm going to simply do now is, basically come up with a probability distribution. So, I mean, I'm just going to use these numbers as my numerators, and I'm going to use the n equaling 60 as my denominator. So these are each of the probabilities for these situations. Many of them I could probably simplify a bit. I chose not to do that just for the sake of easiness. But ultimately, when you produce an answer, you should really simplify it when all is said and done. So you have your probability distribution at this point. So when I go back to the problem again, we took care of part A. I'm going to kind of replace that histogram with this probability distribution. Now I can answer my questions a little bit more easily because I'm looking for probabilities. And it says the first one here, find the probability that given any 3-minute interval in the study, that there is at least 2 and less than 6 customers in line. And so what that translates into is that X is between 2 and 6. It includes 2, because at least 2 means 2 or more, but less than 6 means, okay, I have to be under 6. I could also have put this and said, well, I'm looking for the number of intervals that had 2, 3, 4, or 5 people in line. I mean, there's different ways to reword it as well. But then all I really have to do for this at this point is, just take this, these probabilities in this region right here going from 2 to 5 and add them together. And that's what you're seeing here. And so I end up with 31 divided by 60, which is about 0.516 repeating. Find the probability that any of these 3-minute intervals, there's between 7 and 9 customers. So again, and I'm including both of those. That's why it says inclusive. So I'm looking at these 3 pieces of data right here. So I'm going to add those 3 probabilities together. And I get 13 out of 60, which equals 0.216 repeating. And then find the probability that given any 3-minute interval in the study that there is at most 4 customers. Now, at most 4 customers means 4 or less. So I want the probability of being, 4 or less. So I'm going to go from 4 down to 0 and add these probabilities together. And I get 0.4 repeating 6s. So those are your probabilities for each one of these studies, which, kind of gives you an idea, how many people tend to be in line most often, in these express lanes at this time on a Saturday. Might have to decide, how many they need more cashiers or whatever the case might be. So, for example 5 here, the following table gives 2011 age distribution of the U.S. population. And so what they have here is they have these groups. They're numbered 1, 2, 3, 4, 5, and 6, which basically the numbers themselves really have no meaning. except that, group 1 is anyone under 5, group 2 is anyone from 5 to 19, so forth and so on. So x is going to be this random variable for values 1 through 6. So sometimes you'll have numbers that don't actually represent any kind of measurement or actual count. They're just there to kind of let you know, I could go back and say, okay, well, group 1 is this, So, I want to come up with a probability distribution for this. What I have here are numbers in thousands. And on the second test, some of you, when you were dealing with situations where probabilities were needed, you sometimes just stuck with numbers, and that doesn't always work out for you, and vice versa. Some of you, when you're asked for how many of this or how many of that, you're giving me probabilities. Not the same thing. So for me to calculate these probabilities having these numbers, I should total this up. And when I total this up, I do find there's 306,108, people in this, in this basically distribution of ages here. So when I complete this probability distribution, I'm going to have my groups 1 through 6, and I'm going to have, well, the top numbers are the numbers that were in the table to the left. The 306,108 is the bottom number for each one of them. And those represent the probabilities. They can get they're quite nasty decimals, which is why I kind of leave them as is, because it helps me in the long run. Because when I answer the next question, what percentage of the U.S. population from 2011 was between 5 and 24 years old? Well, I can see group 2 is from 5 to 19, and 3 is from 20 to 24. So basically, this is kind of asking me what proportion or what percentage of the population were in groups 2 and 3. And I can see that's going to be 61,776 and 21,525 added together over 306,108. And if I work that out, I get about 0.2721. And so, translating that into a percentage, I get 27.21% was between 5 and 24 years old in 2011. In Chapter 8, you start dealing with what they call the expected value, but another name for expected value often is average or mean. So, and these are things that you've calculated before. I think just about everybody, has at some point of time through, elementary to high school have encountered the mean, median, and mode. We're going to talk about those in this. So the average or mean is simply just, taking the values of the numbers and dividing it by how many there are. There's two symbols for mean. One of them is X bar, which is this symbol right here. And another one is a mu, which we'll look at later. If you get into a statistics course, X bar usually means it's an average for a sample, whereas mu, which we'll show that symbol momentarily, usually is to take the place of the average for a population. We're not going to get into that far into this course, so it's, basically if you see X bar or you see mu, it means the same thing for us for the most part. The expected value is basically, on average, what do I expect as an outcome? If I know my outcomes go from 0 to 7, but each one of those has a probability of happening, what's the average that I expect to happen, most of the time? So, as a case in point, the number of accidents that occur at a certain intersection known as 5 corners on a Friday afternoon between the hours of 3 p.m. and 6 p.m. along with the corresponding probabilities are shown in the following table. So basically, this is a probability distribution, and you have 0 to 4 accidents in this time range, and about 0.935 or 93.5% of them, at the time, there's no accidents there. 3%, there's one accident during that time frame. 2%, of the time I have 2 accidents in that time frame there. At 1% for 3 accidents during that 3 p.m. to 6 p.m. time interval, and of course 4 means and that value means I have like 0.5 of a percentage point chance of there being 4 accidents during that time there. So you're asked to find the expected value, which means, like, on average, how many accidents would you expect to occur between 3 p.m. and 6 p.m. in this area? If you find that, you know, that you're going to basically have an accident there every day, on average, then you might want to have, like, law enforcement there, or maybe have, an ambulance nearby in there, like, or a rescue team or whatever it may be, frequently, to make sure that, you can take care of the issue there, or maybe you just need to fix the place. So, but I want you to find the expected value. I want to find you the expected number of accidents that occur between 3 p.m. and 6 p.m. in 5 corners using this data. So much as this formula down here shows you, I'm going to take each one of these outcomes and multiply it to its probability, and then add those together. So for our case here, the expected value is going to equal 0 times 0.935 plus 1 times 0.03 plus 2 times 0.02 plus 3 times 0.01 plus 4 times 0.005. And so when I put those together, I get 0 plus 0.03 plus 0.04 plus 0.03 plus 0.02, which comes out to be 0.12 accidents. So on average, I would expect to have 0.12 accidents in this area. So I basically expect there to be between 0 and 1 accidents on any given day, heavily towards the 0. So I'm probably not going to be super worried about this region and not make any special conditions or resources available to take care of it. So if a sample of 3 batteries is selected from a lot of 10, of which 2 are defective, what is the expected number of defective batteries? So we're looking for, if we pick 3 batteries out of this group, on average, how many batteries are going to be defective? So there's a long way of doing that, and there's a short way of doing that for this particular circumstance. Most of the time, and most of the circumstances, you're going to have to do the long way, where you say, okay, I'm going to let x be the number of defects, which means that x can be from 0, 1, or 2. Yeah, I'm picking 3 batteries, but I know that out of this lot of 10, there's only 2 that are defective. So, I can't have x being 3 because, essentially a probability distribution, I mean, if I put 3 there, I would say, well, there's no chance of that happening. Well, I usually don't allow anything on my probability distribution that would have a 0 probability of happening. So how would I calculate these? Well, kind of going back to the way we did it before, this one's saying, okay, the probability of no defects, which means all 3 of them were good batteries, which means that when I chose my 3 out of 10, I'm choosing 3 out of the 8 that were not defective. And that gives me 0.4 repeating 6, which is basically 7 out of 15. Same thing for 1, is I'm going to calculate that, but now, I'm going to have 1 defective. So I'm going to have basically 2 that are not defective and 1 that is. So when I do that probability, I'm going to have 2 out of the 8 that were not defective. I'm going to have 1 out of the 2 that was. So multiply those together over, again, me choosing 3 out of 10 batteries. And I get another 0.46 repeating, which is another 7/15. Now, I could do the formulation for this, for 2 here, which I could say, okay, well, I'm going to have, C of 8, 1 times C of 2, comma 2 for that over C of 10, comma 3. Or I could realize that if I add these together and take that total from 1, I get 0.06 repeating, which is basically 1/15. So now I have each probability, and for each number of possible defects in this choices of mine. So now I'm able to do the expected values. So I'm going to take each one of these x's and multiply it to its probability. And then I'm going to add them together, and I get a total of 0.6 defects. which means on average, I'm going to have 0.6 defects. So that means probably somewhere between 0 and 1, kind of starting to lean towards the 1. So I have an okay possibility of getting a defect out of 3. I'm probably not going to get 2, but most of the time, I'm going to expect probably 1. But getting 0 is not unheard of either. Now, the short way for this particular circumstance depends on the context you have of this. So the easier way for this circumstance, now again, the previous one is what you have to do most of the time. This one here, if you happen to look at this, say, okay, well, I'm choosing 3 batteries. I know that 2 out of 10, or 0.2 of them, are defective. So if I have 3 batteries times my probability of 0.2, I do get 0.6. So, that's another way to come up with the expected value, is I know how many batteries I'm choosing. I know on average what the probability of getting a defective battery is. Now, is this entirely accurate? It's kind of hard to say because of the fact that technically I'm choosing these batteries without replacement. I'm not going to say this is the battery, this is the battery, and this is the battery, and point to the same battery all 3 times. Then I would have a possibility of having 3 batteries that are defective if I did that. So, but for this circumstance, I know the overall probability, because we're saying it's a 2 out of 10, are defective on average. And basically, so you're kind of using more averages here to do that. So because of this circumstance, you can get away with it. But as I said, the easy way for this doesn't work in all circumstances accurately. So the way I showed at first, the long way, is the way you should probably go most of the time to be accurate. Odds in favor of and odds against. As you can see, they're basically, the formulas are just reciprocals of each other. And so basically, when you say odds in favor, the probability of it occurring over 1 minus the probability of it occurring. Basically you're comparing to occurring over not occurring, where this would be not occurring over occurring. So, when you take these 2 numbers together, they should total 1. Usually odds in favor usually have the smaller number on top. Not all the time, mind you. If you have a game that actually allows that kind of thing to happen, then you're lucky if you have, the odds in favor. If you have like a 3-2 in favor, that means, okay, well, I'm likely to have this happen. Whereas a lot of times it's going to be more like a 2-3. It's less likely for it to happen for you. But, these are often used to help you determine winnings and, and to actually analyze games and things like that to see if you're getting fair payouts and things like that. So, let's have a look at this next example. So, for example 3, given that a lottery has a probability of winning the $1 million prize being 0.0000006, what are the odds against you winning? And if a ticket costs $2, what are your expected winnings? So take a moment, think about these questions and how you go about answering it, and see if you can come up with the correct answer. And then we'll go through this. So let's have a look at this. What are the odds against you winning? So odds against here, I have a pretty small probability, so I do expect this to be well over 0. In this case here, knowing that the probability of winning is this 0.0000006, I know that the odds against me winning are 1 minus that 0.0000006 over that probability, which is basically 0.9999994 over that 0.0000006. If you work this out on your calculator using some basic arithmetic, because your calculator will not necessarily turn this into a fraction for you, I can get basically a 4 1,999,997 over 3 fraction, which means that the odds against winning are basically 4,999,997 times to each 3 times that you play, or in this case, every $3 that you spend, or every 3, for each game. If a ticket costs $2, what are your expected winnings? So when I go through this, I have to think of what the outcomes are. And, we're not going into any, lottery games where we have, different outcomes. If you get this many, you might get this prize, you get that many. We're not getting into that here. We're just basically saying, okay, you have a lottery, you get $1 million if you win, and otherwise you don't win. Okay? So our 2 outcomes, based on the description we're given here, is that I can win $1 million, which means that X would be a positive 1 million. Or I could lose $2, basically what I spent on the ticket, and that means that X would be a negative 2. So those are my 2 outcomes. And my probabilities, which I talked about before, the probability of getting the $1 million is that. The probability of getting negative 2 is that. So when I look for my expected winnings, I'm going to multiply these 2 things together and then add the results. And what it comes down to is I get a negative $1.40, which means that a person playing this game, on average, is going to lose $1.40, which is what's going to happen most of the time. You're not going to win the $1 million. So on average, a person loses $1.40 each time playing. So, the odds are really against you. So that's the first way that, when they run these lotteries, that they win. The second way that they win is basically if the odds against winning are 4,999,997 to 3, which means I should get $4,999,997 for each $3 I bet, which basically boils down to I should get over $1.6 million for each dollar I spend, and for every $2 I spend, which is what the ticket costs, I should be getting $3,333,331.33. Hence, they set the odds in a way that, that if your odds against winning, theoretically, if the odds against winning are like this, then for every $2 I spend, I should be getting paid $3 million plus. I'm only going to get $1 million if I win. And so that's where they make out, because even when they're paying you $1 million, they're still profiting $2,300,000. So, so that's how these games of chance, usually favor the house, because even when they lose and have to pay you, they're still winning because they're not paying you anywhere close to what they should be paying you, if you're going with the odds. The probability of an event given the odds, this will show up every once in a while. It kind of deals with between ratios and proportions, but because an odds in favor or even odds against is a ratio. If I say I have a 2 to 3 odds, in favor or against, whichever the case may be, that means 2 chances to every 3 chances. I have me winning versus me losing. Well, that's a probability is a proportion. So, that proportion would be 2/5 and 3/5 because, the 2 and the 3 make 5. And that's what they're showing here. This is the basic difference between the probability, which is a proportion, and odds, which are a ratio. So, if Steffi feels that the odds in favor of her winning her tennis match tomorrow are 7 to 5, what is the subjective probability that she will win her match? So basically, we don't know how accurate Steffi's feelings are and what they reflect, but based off of this, 7 to 5 odds means that 7 times she's going to win to 5 times her opponent's going to win. So that means out of the 12 times we have together, she expects that 7 times out of those 12 that she's going to win the game. And so it's 7 out of 12, which you could make into a decimal, which would be 0.58, repeating 3s. So we talked about, average and expected value, which are essentially the same thing. Averages are good measurements of central tendency, which basically means, like, if I'm looking to see, like, like if I have a group of 40-year-old men and they're doing something, I want to figure out, okay, on average, what's going to happen. Doesn't mean that every one of them is going to do the exact same thing. It just means that, more times than not, they're going to do this, or how many of them are going to do that, that sort of thing. There's other measurements of central tendency other than the average, too. You have the median, which is, if I have a bunch of data, the median would be essentially the middle score. The thing that's in the middle. One of the drawbacks to this is that if I have just random data, I have to put it in order first. And there's a lot of things out there that, if you have data and you put it into a table like a spreadsheet, there are commands to let you put them in order. Even calculators can handle that. The mode is basically, out of the data, which occurs the most frequently. Again, it really helps in order for you to see that, to have the data in order, so you can see, okay, well, how many times is this one occurring? How many times is that value occurring? That sort of thing. So let's have a look at, a situation where you're going to look for all three of these things. So for example 5 here, in an examination given to a class of 20 students, the following test scores were obtained. And more times than not, the data that I would probably give to you is going to be in order, because that's another task that, would take you some time to possibly do, even if you have to put it into a calculator and have it do it for you or something like that. So the data's in order, and you're asked to find the mean or average score as well as the mode and the median. So take a moment, calculate these three values, and we'll go over to see what you compare your answers. So the mean is just, I'm just going to add up all these scores together. If I take the sum of them, I do get 1,480. And I know there's 20 of the students here, so I have 20 scores, which total 1,480. But I'm going to do that divided by 20 to figure out what the average score is. And so that the average score is going to be 74. Now, the median, since it's in order, I want to look and find the middle value. But I have 20 things here. Well, if I have an odd number, I look for the one that's in the middle score. I really don't have a quote-unquote middle term in this sequence because there's an even number here. So what we tend to do in this kind of circumstance is I take this number divided by 2. So what do I usually do to find the middle if it's in order? If it was an odd number, I would divide that by 2. So like, say this was like 21, I would get, basically 10.5, which basically means that the 11th term should be in the middle. Well, for this one here, if I take 20 and divide it by 2, I get 10 exactly. And anytime I don't get a decimal, I get an exact integer. That means that there's really nothing in the middle. So what I have to do under those circumstances, I got to take the 10th term and the 11th term in this case, or take the term number that it comes up when I take, the number of people or things that are in my data, and if I divide that by 2, if I get a whole number, then I gotta look at that number and the term following it and average them together. If I get a value that's a decimal, then if I get like 10.5, that means go to the 11th term. If I get like 14.7, for instance, probably not going to happen 14.7, but I mean it's go to the 15th term, and that's what you're looking for. But for this case here, since if I take 20 divided by 2 and get 10, I should find the 10th and 11th term, which they do happen to both be 80. So if I average those together, I'm going to get 80. So the median score does happen to be 80. The mode is just me looking through the data and see, okay, is there any one piece of data that occurs most frequently? Well, I can see that the 85s occur 4 times, and I don't really have any other value in this group of test scores that occur more frequently. So 85 would be the mode. So you can see there's some differences in these scores here. Which of these three measures of central tendency do you think is the least representative of the set of scores? So take a moment, answer the question, and then we'll go through it. Okay, so when I look at these, these three, what's the best of the central tendency? Well, typically the median is the best. We're not asked for what the best, because because you are looking for the one that's in the middle. So a lot of times median, that's why sometimes you'll see data reported say the median household income, not the mean, the median, because the median also takes frequency into consideration as well, and the more frequent a score is, that's also towards the middle as well. So oftentimes the median and mode are close together. It's not so much in this case because they're 5 they're 5 points apart here. And when I look at the mean and median, that's 6 points apart. So it's like they're not that close to each other. A lot of times though the mode would tend to be the same as the median in a lot of cases, but usually you have to have much bigger data sets than 20. Most oftentimes the mean is the least representative because the mean is influenced by extreme data. In this case, we had some very low scores on this. We had a 40 and a 45. Those 50s didn't help either. Most of the people passed this thing. Most people got B's or above, but yet those several students down here that scored rather poorly pulled it down to a C average. Meanwhile, I still have many more students up here that had a B average. So when I look at, these two here are basically telling me, okay, well, these are at least in the same ballpark as what most of the people in this group had. Whereas this score here is because, well, I have these group of people here that really brought that score down, particularly the 40 and 45. So, and you'll see that sometimes in situations where I have, the scores being moved upward because of the fact that there's one person that scored very, very well, but most everybody scored maybe this. So the mean is often influenced by extreme values. That's why the mean is not always the best measurement. Now, if you take into consideration what we're about to talk about now, then the mean can be used, but then if you say, okay, well, with this other statistic, that'll let me know, okay, well, how accurate is this mean? And that's going to be basically dealing with variance and standard deviation, which are basically measurements of the mean. So, what are variance and standard deviation? The variance of a random sample is essentially, when I take the expected value, and this is the value, this is the symbol mu. Mu is just another way of saying mean. Okay, expected value and mean are essentially the same thing. The variance is basically measuring how far apart each score is individually from the mean. So basically, you see, it's like some part of the calculation. I have P1, which is my probability, times the score, but that score is being subtracted from the mean. So I'm trying to figure out, essentially, how far each one of these scores tends to deviate from that mean score, and eventually that's going to help me figure out whether or not how stable this data is. Standard deviation is just basically the square root of this variance. And what that square root does with the standard deviation, it basically tells me, on average, how far my average is, how well it represents the data as a whole. Typically, the bigger the standard deviation with respect to the data itself, the more erratic my data is, which means that I probably have some extreme values which are really what we call skewing our mean. It's either pulling it up or pulling it down from where it really should be. And of course, the smaller the standard deviation, it means that most of the scores are around that average, and so it's a good indicator of where the scores truly are and how well the mean represents this data. So we have this probability distribution of a random variable, which is given, and you're asked to compute the mean, variance, standard deviation of x. So again, we have these scores and we have their probabilities. So the expected value, or mean, is just going to be me taking each one of those scores and multiplying it to its probability and then adding them together. And so the mean for this is 518. The variance is me going to take, I'm going to take these probabilities, and now that I have this mean to compare it to, I'm going to take each one of these scores and subtract 518 from it, square that, and multiply it to the probability to get my variance. So I would take 0.1 times 430 minus 518 squared, 0.2 times 480 minus 518 squared. So you see the mean is coming into each one of these calculations over and over again. And when I work that out, I get that the variance is about 1,891. So when I do the standard deviation is the square root of 1,891, which is 43.486. Since a lot of this data, when I look at the standard deviation, if I do more of a relative count to that and compare that to the mean, that 43.486 is about an 8% of the mean, which means that basically the data on average, deviates from the mean, by as much as 8 percentage points. Is that a lot? Is that a little? Sometimes it depends on, what certain standards you would set in statistics to deal with that. And most of the time, an 8%, difference is not considered huge. It's not really considered, very reliable either. So, so this standard deviation kind of says that this data does, tend to vary a pretty good bit. So for example 2 here, you're given this information here, and you're asked to find the average mileage and the standard deviation. So see if you can devise a way to come up with that for this circumstance. But one of the things, the mean is pretty even. The average mileage is pretty straightforward because I have these mileages here, these 8 different models and their mileages. So if I just take those mileages and sum them together and divide it by 8, on average, from these 8 cars, they average 44.75 miles per gallon. Now, for me to do the standard deviation, I have to have, basically a probability distribution here, and I really don't have that. I just have basic data here. But it depends on how I look at it, though. Because, I have values that range from 40 up through 50. And I see that 40 occurs once, 42 occurs twice, 45 occurs twice, 47 occurs twice, and 50 occurs once. So if I look at my mileages as my possible outcomes based off of these 8 hybrids, the probability of getting that mileage from these group of cars is a 1 out of 8 for 40 as well as 50, and 1/4 for 42, 45, and 47. Excuse me. You would find that if I took 40 times 1/8, 42 times 1/4, 45 times 1/4, 47 times 1/4, and 50 times 1/8, and added those together, I would also get 44.75. So, so that's another way of handling it, with the probability distribution. But I needed this to do my variance, because I just couldn't say 47 and have to deviate from the mean each time, because theoretically I could, but one of the issues I would have is that I don't have my p-values that, from the formula for me to calculate. So when I set this up, the variance is going to be 1/8 of 40 minus 44.75 squared, 1/4 times 42 minus 44.75 squared, etc. for each one of these mileages here compared to the mean, and with each one of their probabilities outside. And so when I work this out to get the standard deviation, I'm just going to square root all this information, and it ends up being about 3.072 miles per gallon. So basically, is this a big deviation here? You're looking at about 6 or 7% difference. That means that, on average, these are, different by as much as about, 6 or 7 percentage points. Again, not a huge difference, but not, because this is like considered statistically insignificant either. It's better data overall than some of the other things we've seen so far, in comparative. But generally, we do expect to have some deviation from the mean, which is 44.75. You can see we do have some values that are a bit bigger, and we have ones that are a bit smaller too. So, example 3. The number of married men in thousands between the ages of 20 and 44 in the United States is 1998 is given by the following table. So you have age ranges. You have 20 to 24, 25 to 29, 30 to 34, 35 to 39, and 40 to 44. And you have the number of men, which is, I'm not going to read them all off, but there they are. So this table is not a probability distribution. I'm going to need a probability distribution in order for me to help answer this question. So that's going to be a hint for you, because you're going to have to figure that out. Now the problem is, how do I figure out that probability distribution? Because I don't just have, ages 20 to 24, I know there's 1,332 men, but I don't know what their ages are. I don't know if how many of them are 20, 21, 22, 23, or 24. I just know that in this age group, I have 1,332. So how do we get around that, or how do you think we get around that? And then again, we have numbers here. We need probabilities. So take that into consideration as you attempt to find the mean and standard deviation of this given data. So when you deal with a situation where you're given basically ranges of scores or ages or whatever the case may be, what you need to do first is that you need to basically come up with a representative from that group. And so basically what you do is, I'm just going to average these two numbers and for each one of these. So if I average 20 and 24, I get 22. Do the same thing for 25, 29, I get 27. You kind of see the pattern at this point. So these would be the numbers I use as representatives as my X value. So I take the average age for each one of these subcategories. And of course, what I need to do is I need to total up this number here of men that were in this, data, which ends up being 27,127. And so when I set up my table here, I'm going to have my 5x values that I took by doing the averages of the minimum and maximum of each range. And then I'm just going to take these numbers and divide it by the total of those numbers to get the probabilities. So I have these. These decimals would be kind of on the nastier side as far as being able to terminate them at a certain place or round them off. Even if you go to 4 decimal places, it may not be that super accurate if you are rounding throughout this entire thing. So you're going to see as I compute this data, I'm going to keep the fractions intact, whereas it's not 100% necessary. I'm just doing it for accuracy's sake. If you want to round it off to 4 decimal places for your probabilities, you probably find out that the answer I'm going to show and the answer you would get are very similar. So as far as the mean goes, I'm going to take each one of these and multiply it to their probabilities. So 1332 over 27,127 times 22, so forth and so on. And when I add those together, I get about 34.9456 years old. So in this study, on average, the average male in this study is about 35 years old. So they would be falling somewhere in this region right here. Not quite, but since their ages, I'd probably say more towards this age right here. And you can see that. The data, most of the data is in these last two groups, and not as much in these first three, I should say. Now, as far as the standard deviation goes, I'm going to take these same probabilities, I'm going to take these same values, but I'm going to subtract this mean from them and square it, and then of course I'm going to square root that sum. So I'm showing basically how the use of the formula, and when I figure that out, the standard deviation is about 5.938 years. So on average, 6 out of 35 is about a 17% difference. So this data seems to be deviating quite a bit, but that's mostly because I don't know what the actual ages of these men are, because they're categorized by a group. And that sometimes happens with standard deviations, is that it reflects the fact that I really don't know. I mean, because, I can see that, as I move from age to age, just alone, I'm going by 5-year intervals here. It looks like I'm just taking 22, 27, 32, 37, and 42-year-olds for the study, but that's really not what's happening. But that's the only way I can really represent the data and get a probability distribution. So there is how you do mean and standard deviation under 3 different circumstances. So use that as you go through and do your practice problems and try to make sure you're handling those correctly. If you have any further questions, please bring them up in class. Until next time, have a good day.